All right, welcome everyone. I'm sure we've had a long day and we've probably had almost more astronomy than we could possibly handle, but well, it's almost an oxymoron. We can never handle too much astronomy. So I'm going to be talking about what I think are some of the big questions. They won't be all the questions, but it will be what I think are some of the big questions that we are working on now and into the future, and I'm going to give you a sense of what we know and what we might not know. So, some big questions. What are planets like beyond our own solar system? Now that we've ruled Pluto out, we've taken care of our own solar system. How big is the universe? As I'll show you, that's also about how old it is. And how did the universe evolve into what it looks like today? We're here, but we weren't born as part of the universe. We sort of evolved out of the universe. And these are the big questions we're trying to answer over the next several years and have been trying to do over the last few years as well. So, big questions. What are exoplanets like? Here is a list of the latest catalog of planets from yesterday. 1,822 planets discovered beyond our own solar system. And those are in 467 of those are in multiple planets. And I like this one because right here, right where you can't see it, I helped discover that one, the one that's in the black there. And that planet was discovered with the HAT South telescope, kind of a funny looking thing in a shed that comes open. And there's 2 more of those telescopes in different parts of the world. And those help us find, and I'll show you how we might find planets with those. But we have a lot of planets out there, and while every planet is sacred, some are more interesting than others, and we'll talk about those as we go along. So how do we find planets? We find planets 2 ways at Siding Springs. Both, we are required to use the fingerprints of atoms, and so when we go through and spread the colors of stars out into the colors of the rainbow, we see the fingerprints of the chemical elements that they're made out of. Helium was discovered in the sun before it was discovered on Earth. That's why it's called helium, the Greek word for the sun. And so every chemical element has a fingerprint. Furthermore, those fingerprints are very precise colors, and our instruments are amazingly good so that if an object is moving, those colors will shift a little bluer if they're moving towards you, a little redder if they're moving away, and we can measure the velocity of a star this way on the other side of the galaxy to about this speed, about 1 meter per second. We can measure a star on the other side of the galaxy to that accuracy, and that allows us to find planets. And so if you have a planet orbiting the sun, so let's just say the Earth, it goes around, and down here, and I'm going to go here so you can see it, the spectrum, that colors shift back and forth as the planet goes around. Why? Because as the planet goes around the sun, the Earth's going 30 kilometers per second right now around the sun has to counteract ours, and so it's 1,000,000 times more massive, so it moves 1,000,000 times slower, so it's doing a little circle. But it's doing a circle about as fast as I'm walking through space, and that we can detect. And it turns out the bigger the planet, the more the motion. So we can actually find things by these little loop-de-loops that the sun, their suns, are making. So here at the AAT, we have this amazing spectrograph that's been around for a long time that can do those measurements to how fast I walk of distant stars. And I don't think you get a chance to see this because it's a very sensitive instrument, which if you sort of blow on it the wrong way, it gets the wrong answer. It's got to make very precise measurements. The other way, and this is the way I helped discover that planet that you couldn't really see, is using the same way that the British decided to claim Australia for the homeland, where they sent Captain Cook to go out and see Venus when it went in front of the sun. And it did that back in the 1760s, and it did it just a couple years ago in 2012. And won't do it again in my lifetime unless I live longer than I'm expecting. And when it does that, when Venus goes in front of the sun, it blanks out a little bit of the sun. And so if you were looking at that star, at our sun from the other side of the galaxy, when Venus went in front of it, it would get a little fainter. And so that's the purpose of this telescope, the Hat South telescope. And so it's 4 little telescopes that are pointed in different directions. It's not just 4, there's another set of 4. So there's actually 8 telescopes. And they can look at a piece of sky that's 128 square degrees. So that is roughly 500 times the size of the moon. And we can monitor about 1 million stars at a time because it's very rare for a planet to go in front of their star. So we need to look at a lot of stars to find the rare occurrences when that happens. But it's a really good way to find planets. And here is our first one. We found now about 20 of them, although only 6 are official. So there's 14 more coming out. You can see this is when its star, this is a planet bigger than Jupiter, went in front. It dipped a little bit and then went on its brightness. So we can find those. Now the United States put up a satellite known as Kepler to do this. And space has some advantages, which is that you don't have the nasty atmosphere between you and the stars. And the atmospheres makes things jiggle a lot when we look at them. So we can't make as precise measurements on the ground normally as we do in space. So Kepler was able to go through and look at a bunch of stars itself, and it discovered a whole range of planets. Most of the planets that have been discovered are with this mission. There's a problem, though. The mission discovered a bunch of really faint things that are kind of hard to study, and the mission cost about $1 billion. That's a bit of a problem as well if you want to do it again. And the other problem is when you're in space, and your little wheel that causes you to be able to point steadily in the sky breaks, then you tend to do this. You're sort of like a helicopter that loses your rear flywheel, and you tend to go in circles. And so Kepler is now going in circles, and we're still trying to take pictures with it, but we're not able to discover planets quite the same way as it intended. So it did its 3 years, but its ability to really find planets like it was, those days are over now. But it did find over 1,000 planets, including some really interesting ones that look a lot like Earth. If I plot what that found, this is how big the planet's radius is compared to the Earth. So if it's 1, it's the same size as the Earth. And this is how long it takes for the planet to go around its star. And so you can see 365 days, it didn't quite get down to the Earth proper. We're going to have to wait for the next mission, or hopefully we'll get lucky here in Australia, we'll see. But we did find some things that are kind of interesting. These things right in here are what we call super-Earths. They're objects that are like Earth, just bigger. We think they're made out of rocks, and a lot of them are in the place where water will be liquid. That's a place where life like we know it could exist. So we think there's some chances out there for life to exist. Is this something we should think more about? Well, the answer is yes. And how are we going to do it? Well, we're going to do it with new technology. And some of the technology we use involve lasers. So Australia is part of a telescope consortium known as Gemini. It involves a telescope in Hawaii and one in Chile. And it turns out up in those very high mountains, up at 4,000 meters, we can get rid of some of the effects of the atmosphere that we find very hard to do here at Coonabarabran. And so with this laser, we can go through and correct the stars and get rid of the twinkling. And when we do that, you can make an image. For example, this is the planet Uranus. Uranus has rings, and that's with the atmosphere normal, and that's when you turn this magical system on. A system we're actually using at Mount Stromlo to try to manage space debris so that we don't have gravity in reality, the movie in reality. And we're also using in places to go and help do eye surgery, because when they take a laser and go through your eye has turbulence just like the atmosphere does. You use that same basic technique. So one of the things you can do is you can go look for planets. And here's a brand new instrument that Australia is part of. And you can actually literally see the planets around other stars now with this technique. With bigger telescopes, we're going to be able to do this even better and really being able to look at planets directly. In the future, we have these 2 major satellites, which we will be participating in, that are going to be looking at literally every bright star in the sky for these transits. Why are transits interesting? Well, let's look at Venus. This is a real picture of Venus when it was in transit. And you have Venus in front of the sun, but look right here, that little rim. That's sunlight. And that's sunlight that's being bent around the planet through the atmosphere, through refraction. And so when that light goes through Venus's atmosphere and comes to us, it picks up the chemical signatures of the atmosphere. So we can see what's in Venus when it's in transit, if we have a really big telescope. And so why would that be interesting? Because it turns out humans, for example, make things like CFCs and all sorts of other things, which you might detect us this way. But life itself produces oxygen in large abundance, and we don't know of any other way to do that except for things like plants and animals to do that. So this is a way to actually, and this is going to happen in the next 10 or 15 years probably, we're going to be able to go out and look for life on other planets. And to do that, we need a big telescope. And we have a big telescope on the way. It's known as the Giant Magellan Telescope. And it's a telescope that is 24 meters across. So that's about the size of this room. Okay? So it's 36 times more collecting area than the AAT. And it's got these 7 mirrors, each one 4 times bigger than the AAT's mirror. And you can see how big this thing's going to be compared to a semi-trailer. It's huge. This is going to be able to start looking at the sky, we think, in about 6 years' time. And it's going to help us use the discoveries we find here and in space to look for life. So let's move to another big question. If that one wasn't big enough, how big is the universe? Well, it doesn't get any bigger than that. And it turns out this is a question that we've sort of answered. But in answering it, we've ended up with more questions than we started with. So it turns out that we can measure how big the universe is because the universe is expanding. This was learned by Edwin Hubble, who measured galaxies. And this is his real figure from 1929. And he measured the distances to galaxies, and he measured how fast they were moving away from us from that Doppler shift. And what he found is the further away the object was, the faster the motion. And with that knowledge in hand, he said that means that the universe is expanding. And why did he say that? Well, if you've got a universe, and through the magic, you expand it. Sorry, this machine's messing it up just a little bit. When I overlay before and after when I've expanded the universe, what do I see? I see that nearby objects have moved a little bit, and distant objects, they've moved a lot. When you expand the universe, the further away you are, the faster you move away, just like what we see in our own universe. Now imagine that the universe is expanding. Well, let's put it in reverse. We can figure out if we put it in reverse, then it'll tell us when the Big Bang happened. We look at how much it's going now, and then we go in reverse and we say, how long would it have taken for everything in the universe to be on top of everything else? So let's think of it graphically. If I put 2 galaxies right now, some distance apart, if the universe is just expanding, we run it in reverse, and that's the time of the Big Bang. All right? And you can see if the universe just keeps expanding, it gets bigger and bigger and bigger and bigger without end. The universe is infinite into the future. But we know the universe is full of galaxies, and it's full of us, and we have mass, and we pull on everything. So everything in the universe is going to pull on everything else. So we expect the universe to be slowing down over time. Now, we don't know how much it's slowing down, or actually we do now, but we didn't 20 years ago. And you could imagine a universe that's slowing down won't be as old, but it might slow down so much that it'll stop expanding and go into reverse. So this possibility of the universe is something to contemplate. You have a Big Bang to begin with, but we don't really know what we end up with. Do we have a universe that goes on forever, or do we have a Big Bang in reverse? Big questions. Well, we sort of know the answer to this, and this is work that I have worked on and other people here have worked on. And it's interesting because space is complicated. It's actually 4 dimensions, not 3. This is what Einstein is really famous for. You think he's famous for E = mc². Well, he's famous for that too, but he's really famous within physics because he realized that gravity curves space. And if you have a heavy universe, space curves onto itself in the shape of a giant four-dimensional sphere. Now, if you're having trouble to envision 4 dimensions of sphere, it's okay. I can't envision it either. I just have to use mathematics to understand how to navigate around this space. A light universe has a different shape, bends away from itself, and there's the just right universe, the universe that has just the right amount of stuff, that it goes on in all directions without curving at all, and that universe is infinite. This universe is finite. This is a universe that stops expanding in the future and ends. It's finite in space, and it's finite in time. This universe is infinite in time and infinite in space, as is this universe. The more stuff you have, then you go from here to there. All right, so in 1998, I led a team that went out and measured how fast the universe was expanding back in time, thinking if the universe was really heavy, it would slow down, and we could weigh the universe by measuring how much it slowed down. So here is what we were expecting. We were expecting the universe to lie somewhere between here and here. If it was on this line, the universe just expands forever without slowing down at all. If it follows this line, then the universe is right in that place where it sort of comes to rest in infinite time in the future. If it's down here, then the universe ends in the future. But what we found was an unexpected surprise, which was that the universe was actually expanding slower in the past and had sped up. And that was a big surprise indeed, and the only way we can explain it is from an idea that Albert Einstein had, which is that space can have energy. Now we know atoms, we have something we call dark matter, which we'll talk about in a second, but we need something which makes gravity push. And it turns out if space has energy, that makes gravity push rather than pull by Einstein's equations. So we often call that dark energy, also known as the cosmological constant. All right, so here at the AAT, my colleagues in Australia, when I made this discovery, or I will say finding, I would say there was some skepticism. And they said, we need to go out and see what the universe is really doing. And so they used this telescope for 5 years, and they made this map of the universe, which is right here. And so they could go in and they could ask themselves, I'm going to put different types of stuff in the universe. I'm going to make different universes here in the computer. We're going to observe the universe, and we're going to try to figure out which one of these is the universe that we live in. So when they made this measurement back in 2001, what they found is, can you guys look and figure out which one of these 4 pie-shaped wedges looks like the real data? Everyone think? Your eyes can usually do this. We use a computer to do it. Well, the one the computer tells you is that one. If you didn't get it right, okay, we won't make you do this work in the future. But what it said was that the universe, to look like that, had to be about 80% stuff we call dark matter, stuff that seems to only have gravity but doesn't have pressure in the normal sense, and 5% atoms, 30% of just right, the just right amount to make space flat so it doesn't have curvature. That's what we found from this measurement. It was essentially 25% of the way to make the universe just right in dark matter and 5% in atoms. Now that didn't contradict our measurement because it turns out this experiment was pretty blind to dark energy. Energy is part of space. It really doesn't make much difference in what you see. It's much more subtle than this experiment could see. And so this dark matter stuff, which has been Ken Freeman saw in galaxies in 1970 for the first time, and Fritz Zwicky saw in clusters of galaxy like Warwick Couch just showed you in the 1930s. Well, it seems to be with us, and we think it's some undiscovered particle that literally can go right through the Earth. And last week I was in Stawell in Victoria looking to work with the Italian groups and a group down in Melbourne to put a detector underground where the only thing that can get to it is dark matter. And our thoughts are that dark matter might very, very rarely smash into an atom and then you can see it. And so in the Stawell mine, about a kilometer underground, we're looking at maybe doing an experiment to see if we can detect this. All right, the other experiment is from looking at the earliest picture we have of the universe, the cosmic microwave background. And what we see in this picture are sound waves splashing around the universe. And so those sound waves, it turns out, tell us a lot about the universe. And why is that? Because it turns out the Big Bang seeded, it sort of put little ripples in the universe. And so think of the universe as a big pond, and when you put a ripple in it, the wave action depends on what is in the pond. A pond of molasses is different than a pond of water. And so when you look at that early universe, the Big Bang put lots of gravel into the pond of the universe, and we see those splash marks now when we look back to that cosmic microwave background. And those splash marks tell us a number of things. They tell us what the universe is made out of, and it turns out the size of those splash marks also tell us the shape of the universe, because if the universe is curved, it distorts the size of the ripples of space. So you can measure very accurately what the universe is made out of and the curvature of the universe. And what we find, it turns out, is the universe has no curvature. It's within a very, very small fraction of a percent of being exactly just right. It also tells us that the universe has got to be made of 25% dark matter and 5% atoms, just like all the other experiments are indicating, it seems. So when we put it all together, we seem to have a universe which is about 13.8 billion years old, but is made up of all these crazy things, 95% of stuff we do not understand. But it is able to predict exactly what we see. And so although it's rather unsavory in terms of what we would like in a theory, we'd like to understand it all, like it or not, within science, when something predicts everything that you see, that's the theory you use. And although it's probably not perfect, in the same way Newton's laws of gravity were not perfect, it's a pretty good approximation at this point, and I don't think it's going to go away. All right, so how big is the universe? Getting back to our question, it's 13.8 billion light years, not light years, it's 13.8 billion years across. When we look out to this cosmic microwave background, which turns out happened right after the Big Bang, and takes like 13.8 billion years to get to us. But I told you the shape of space is that it's flat. It doesn't curve. It's not finite. Space is infinite. So there is almost certainly stuff out here that we can't see because its light has not been able to reach us. And amazingly enough, because the universe is speeding up, it will never be able to get to us because the universe is getting bigger faster than light can get to us. And that's rather disappointing because there's all this real estate out there we're never going to be able to get to. All right, so that's the part we can see. Now, let's look at one of the other things that we can do here at Australia. One of the things that Australia has done is really led this cosmology area for a long time, and the 2DF Redshift Survey is now teaming up with our sister telescope in Chile to do an experiment where we can literally look back in time at those sound waves. And this is known as baryon acoustic oscillations, and we can see those sound waves imprinted in the galaxies of today. And that experiment is a place where, as Australia has led, we're sort of been overtaken recently by the United States, but it's literally driving a measurement, and here's the measurements that my method using supernovae measured in gray, and these are the measurements from this sound wave measurement, and they agree exactly. They're almost too good to be true, actually. So everything seems to hold together. The European Space Agency has this huge satellite, Euclid, that it will be launching at the beginning of next decade to carry these experiments out further, driven, again, by a lot of this Australian research. I just wished we had $1 billion to spend on stuff like the Europeans do. All right. Finally, let's finish off with the life of the universe, the life and times of the universe. So this is a picture of the universe when it's 380,000 years old. And it fades away because the universe is expanding, and as it expands, it cools. And at some point, the universe looks like this. It lights up. Now, we haven't seen that yet, but we know it must have happened. So this is the picture of the universe when it's 10 million years old. If you don't see anything, that's because there's nothing to see. It's dull, it's lifeless, nothing there. And so we have the opportunity now to go through and look at that time using radio, because when you have a hydrogen atom and the electron, which is like a top, flips sign, it puts out a radio wave. And so that didn't work. So at the end of the dark ages, as we call it, the universe will be emitting all those radio waves, and those radio waves get destroyed by all the stars that are created. So our hope is that we can see that process, and this is an animation of that process, through a new radio telescope in Western Australia, out truly in the middle of nowhere, in a shire of 160 people over, many, many tens of square kilometers. And out there we have a radio telescope that is going to be mapping this. It's mapping it right now. We haven't seen it yet. And it is all in preparation of a telescope that will eventually be called the Square Kilometer Array. I normally have the sound turned off. But we can go with big telescopes like the Giant Magellan Telescope and literally look back in time. So this is what the Hubble Space Telescope sees when it looks back about 12.5 billion years. With the Next Generation Space Telescope, known as the James Webb Space Telescope. Sorry, I'm a little slow on this one. It'll click here eventually. It'll probably go 3 ahead, because I've been impatient. There we go. The James Webb Space Telescope. So it's about 2.5 times bigger than the Hubble Space Telescope. It'll be launched in 2018. We're going to be able to look back further, and we're going to be able to use the Giant Magellan Telescope to go through and follow up as Australians of all the first stars that it can find. It has so much power, we should literally be able to look back to that epoch of the first stars. But as I said, I'm impatient. And so we've got all the first stars in our own galaxy just around us. And so using the Sky Mapper telescope, which is up on the side of the hill, we can go through and we hope figure out stars because they have only hydrogen and helium in them. This is the nuclear reaction calculations of the Big Bang. And you can see there's hydrogen, there's helium, a little bit of beryllium, lithium, and that's it. So with the Sky Mapper telescope, we're able to go back and use Australia's largest digital camera to look for objects that literally have no iron. And so last year at the Bach lecture, I told people we had this up our sleeve. Well, we did announce it. It's the first star discovered with no iron in it all. And we're hoping when we do the entire sky, we should find a lot of these things. And we'll literally be able to see, as an archaeologist looks around, how our galaxy was formed of the first stars. So this is a great harbinger of things to come, we hope. All right. And to finalize, I'll just say that we work hand in hand with the AAT because their instrument, the Hermes instrument, is all about doing the chemical identification of all the stars in the sky. So Sky Mapper is going to be able to identify them, and Hermes is going to be able to do the real DNA fingerprinting of them. And together we hope we should be able to learn how the universe got started in all these different ways. All right, so it's an amazing place here. We have an amazing set of instrumentation, and it's kind of interesting to see how we drive things because the most recent European satellite, again another $1 billion satellite, is really driven by the work being done here in Australia. It's known as Gaia, and it's great to have them spend that money because we get to be part of it as well, and I promise you we have not spent $1 billion on this. So I think I better stop there, just reminding you that astronomy is the frontier of science, and I don't see that changing. There is much more out there that we don't know than what we do. Thank you. Is there anything we can know about the universe beyond? We have to extrapolate. So we can, to first order, assume that the universe beyond what we can see is like what's inside. And we know that if the universe is well behaved, that it should look almost exactly like what we see. One of the big questions we have is the universe changing a bit as we look further and further away? And there were some measurements made by Australians which indicated it might be. I've talked to them recently and they said, it seems there's something funny going on, and the universe actually looks exactly the same. It's so boring. Every part of the universe looks exactly the same as our little part. So it's very tough. If you don't get any information, you really are extrapolating into the realm of metaphysics rather than physics. Physics is testing your ideas, not just pontificating your ideas. Yeah. Okay, so that star is roughly about 5,000 light years in distance, so that means it's moderately close. It's neither close nor far away. It's sort of a reasonable distance away. So the age is very hard for us to measure. We assume it's very near that 13.5 billion year old mark or so. It's in our own galaxy. We get more, we'll be able to learn more. One is always tough. Yep. Yeah. So, right. Okay, so the question is, did dark energy drive the inflationary period? Now, I didn't talk about inflation here. Inflation is an idea that the universe started expanding, accelerating, when it was very young. How young? Decimal place, 35 zeros and a 1. This is what is the Big Bang. We don't know what happened before that at all. So when we talk about the Big Bang, we talk about when the universe seems to have expanded from the size of a golf ball to the current size of the universe in that very tiny instant of a second. That's what happens when the universe accelerates. We need some sort of dark energy to accelerate the universe. But for whatever reason, that dark energy then went away, so the universe could slow down and become a place where we could live. A rapidly accelerating universe is not a place where the Earth could have formed, because all of the atoms of the Earth would have been so far away they would have never been able to form together. Second part of the question? Oh, so it got very big, and it may be much, much bigger than what we can see. So it's hard to tell. You know, infinity is a big number, and we don't know if we're on this side of infinity or on that side of infinity. It's close to infinity. Yep, in the back. No. So antimatter is stuff that, quite frankly, is a lot like us. It turns out that every particle has an antiparticle. Sometimes that particle is its own antiparticle. So light, for example, can crunch into itself and annihilate if it has enough energy. So protons, there are antiprotons. Electrons, there are positrons. Now, fortunately, the universe is not full of a lot of those, because when we meet each other, we annihilate and produce lots of energy. For some reason, not understood, in the early universe, there was more matter than there was antimatter, and so we have a universe made of matter. I promise you, if the other side won, we'd still call it matter, though. All right, you've got one burden question? Yeah. Multiverse, yes. That's metaphysics. I look at it as metaphysics, and unless someone can come up with a way to test it, one way you might test it is if you see the properties of the universe drifting away, then that would indicate that as you moved outside of the part of the universe we could see, the laws of physics would change. Of course, as people would have seen a couple of months ago, there was the idea that the Higgs boson has this field of energy associated. Dark energy, just not very much of it. But it could become unstable and run away, which means that the universe would suddenly, parts of it start accelerating. The problem is, it all happens at the speed of light. So if that's going to happen in our universe, which I don't think it's going to, we'll never know about it because we would suddenly be whipped to pieces at the speed of light, and you can't see something moving at the speed of light come towards you. It just, suddenly you're gone. So if it ever does happen, we'll have no idea what hit us.